Our next lesson on area is going to start with a figure that you may be familiar with, or at least you may be familiar with the formula already. So this is going to look a little bit at the background of where it comes from. There are a few different ways to find the area of a trapezoid. One way is to draw a line from here straight down, creating a rectangle and a triangle, calculating those areas separately, adding them together to come up with the whole thing. I'm going to use what I think is a little more clever way to do this. Recall the parts of a trapezoid. Here we have a base. Here we have a different base. Those are the two parallel sides. And here we have a height. Now I'm using a right trapezoid, meaning we have a right angle here and here, but this also would work for any trapezoid. And I'll show you the difference shortly. So what I'm going to do, in fact, what I have done, is I made a copy of this trapezoid and I rotated it 180 degrees. And you get this. So now I have two equal trapezoids. One has been rotated 180 degrees. And if I put them together, I end up with a rectangle. So I will call this trapezoid A. Here's A again. Here's A again. It's copied. Here is our base 1. Here's our base 2. Here's our height. When I rotated it 180 degrees, base 2 and base 1 flipped. And now, because this was a right angle, this is a right angle still, I end up with a rectangle. This rectangle, we can say is length times width, only the length is base 2 added to base 1, and the width is now the height. That's not the area of a trapezoid. That's the area of both of these combined. All I have left to do is divide by 2, which means multiply by a half. And usually we write it like this: 1/2 B1 plus B2 multiplied by the trapezoid's height. And as always, in fact, this is true no matter what, the base and height must be perpendicular. So that is where the formula for area of a trapezoid comes from. Now, what happens if this trapezoid does not have a right angle like ours did? Well, we get the same thing essentially. So let me create a trapezoid without a right angle. That's not a good trapezoid. That's not what I want either. Here's a trapezoid that has no right angles. So as I clone this, flip it around 180 degrees, instead of a rectangle, I will get a parallelogram. But it still works because here's B1, B2, there's the height, B2, B1, and this height, recall, has to be true for the entire figure. No matter how far left or right I go, that height will not change because these two sides have to be parallel. The distance between them never changes, so the height of that object never changes. So it still works, only instead of getting a rectangle, we would have ended up with a parallelogram. You still come up with the same formula. Two of these trapezoids equals the whole thing. One trapezoid is half of that whole thing. That is the area of a trapezoid. Now the next two may be new formulas for you. We have a rhombus. And yes, a rhombus is a parallelogram, so why doesn't base times height work? It does work. But with a rhombus, you're not always given a base and a height. So we're going to look at an alternative way to look at a rhombus. So first thing I'm going to do is to draw in these segments. You know them better as diagonals. And we know that with a rhombus, the diagonals are perpendicular. And that's the key to this formula. We also know that because a rhombus is a parallelogram, these diagonals bisect each other. I will call these two pieces X. I will call these two pieces Y. And I'm also going to come up here and say that diagonal 1 is 2 X's. So I'll call this diagonal number 1. Diagonal 1, it's 2 X's, X plus X. Here's diagonal 2, it's 2 Y's. That'll come in handy in a little bit. The way I'm going to look at this area is I have a triangle here. And the triangle I'm looking at is really the combination of these two. So I have this large triangle. And I have this large triangle. I have those two triangles. The first triangle has area, here's its base, 2 X's, and here's its height, Y. 1/2 times the base is 2 X's times the height, Y. This triangle down here, here's its, one more time, it has base 2X, it has height Y. So it's really the same thing. There's our area of this rhombus. And now we just have a little bit of algebra to do. Half of 2x is just x. So we get xy, and then we get xy again. And it ends up being 2xy. And now I'm going to use these two definitions up here. 2x is just diagonal 1. Diagonal 1 is just 2x. So here we go. Y is left over, but I don't want to use a y. I want to use this. Well, I know that diagonal 2 is 2y. So y by itself is half diagonal 2. And now we have what we're looking for. For a rhombus, instead of using base times height all the time, an alternative formula is 1/2. If we rearrange these terms a little bit, I should put an equals there. 1/2 diagonal 1 times diagonal 2. Oftentimes with the rhombus, you will be given diagonals and not base and height. If you are given base and height, use those. But another form that works for a rhombus is half the product of the diagonals. The reason that works is because the diagonals are perpendicular. And that's what makes this formula a little easier to use. One final formula to take a look at for this section. area of a kite. Again, I'll start by drawing in both diagonals. We know that a kite's diagonals are perpendicular, just like in our last figure. Only now, the diagonals of a kite do not bisect each other. Only one diagonal is bisected, this one. It's the diagonal that connects the two equal angles. These two angles of the kite are the same. These two angles are not necessarily the same. So I end up with some different measurements here. X and X. So again, I'll call that diagonal 1. The diagonal 2 is going to be whatever Y is plus whatever Z is. Let's look at the area of this kite. This triangle, and then this triangle down here. So I'm splitting the kite into two larger triangles. This top one, which is not half of the whole thing, and this bottom one. This top triangle has area 1/2. The base is 2x, the height is y. The bottom triangle has base 2x, height z. So this one's going to be a little different potentially. A little bit of algebra work here, xy, and then this will be xz. And we need a little more algebra to finish this off. I'm going to factor out an x from both terms. And now I see that diagonal 2 just showed up. This y plus z is exactly diagonal 2. And I have 1x left over. But if I go back to the top, if diagonal 1 is 2 x's, 1x is half diagonal 1. And it turns out that the area of a kite is exactly the same as the area of a rhombus. A little bit of rearranging and we're done. X turned into 1/2 d1. Y plus z is just d sub 2, and we have our area. As always, completion quiz, post questions, and that concludes this section.